Welcome to today's explainer. I'm absolutely thrilled to be diving into this topic with you today because honestly, it's going to completely shift how you look at the world. Today, we're exploring mixtures and how we separate them. I know it sounds like something strictly confined to a high school chemistry lab, but the fascinating reality is that almost everything around us, the air we breathe, the food we eat, the medicines we take, is a mixture just waiting to be understood.
Like, really think about it for a second. Have you ever wondered how we get pure, white, sweet crystals of sugar from a tall, green sugarcane plant? Or how doctors can detect a disease like malaria using just a tiny, single drop of blood? These everyday miracles rely entirely on the abstract science of separating mixtures. It's literally the invisible engine powering the things we rely on every single day. So here's our roadmap for today. First, classifying everyday mixtures. Second, solutions, suspensions, and colloids. Third, concentration and solubility. Fourth, the art of separation. And finally, chemistry in the real world. All right, let's kick things off with Section 1, classifying everyday mixtures. So, what exactly makes a mixture a mixture? By definition, it's a physical combination of two or more substances. And the absolutely crucial point here is that word physical. These substances aren't chemically bound together. They're just, sharing the same space. And because they're just hanging out together, it means we can use physical methods to tease them apart again. Now, mixtures generally fall into two main camps. On one side, we've got homogeneous mixtures. Think of a perfectly stirred glass of sugar water. The very first sip is exactly as sweet as the last one, right? Because it has a perfectly uniform composition throughout the whole glass. On the flip side, we have heterogeneous mixtures. Imagine stirring a handful of sand into a glass of water. The composition is totally non-uniform. It's chunky and you can easily see the separate sand particles just settling out at the bottom. Moving right along to Section 2, solutions, suspensions, and colloids. This brings us to something super cool called the Tyndall effect. You can see this brilliantly when a laser pointer passes through different beakers. In some mixtures, the beam is basically invisible. But in others, like if you mix a little milk with water, the light scatters off the particles, making the beam glow brightly. It's like magic. And you've totally seen this exact same science happening at a massive scale. Think about stadium floodlights scattering off dust and smoke in the night air. Whenever invisible particles in a mixture are just large enough to scatter a beam of light, you're witnessing the Tyndall effect in action. We can map out this whole spectrum of particle size perfectly. Down on the tiny end, we have solutions, like our sugar water from earlier. The particles are incredibly small, less than a nanometer. They don't settle, and they don't scatter light. On the massive end, we have suspensions, like muddy water. The particles are huge, over 1,000 nanometers, and they'll drop straight to the bottom if you leave them alone. But right in the fascinating middle, in that Goldilocks zone, we have colloids. Think of stuff like blood or milk. Their particles sit right between 1 and 1,000 nanometers. They don't settle out, but they are just big enough to cause that brilliant Tyndall effect we just talked about. Okay, jumping into Section 3, concentration and solubility. When a chemist asks, hey, how much solute is dissolved in this solvent? What they're really asking for is the concentration. And we typically express this using three main percentages. We've got mass by mass, which just compares the weight of the solute to the total weight, mass by volume, comparing weight to the liquid volume, and volume by volume, comparing two liquids. Now, I know that sounds a bit technical, but I guarantee you've seen these before. Seriously, these formulas aren't just locked away in a laboratory. They are literally sitting in your kitchen pantry right now. A box of milk powder uses mass by mass percentage to show you its nutritional makeup. An intravenous glucose drip at a hospital, that relies on mass by volume to ensure a patient that's the exact right amount of energy. Even a standard bottle of white vinegar uses volume by volume percentage to show it contains exactly 5% acetic acid. This math is everywhere. But of course, there's a limit to how much stuff you can cram into a solvent, right? That limit is called solubility. And temperature is basically the cheat code to unlock a solvent's capacity. If you look at how compound B behaves on a solubility curve, it's wild. At 20 degrees Celsius, the water can only hold about 200 grams. But if you heat that water up to 60 degrees, suddenly it can hold nearly 300 grams. For most solids, just cranking up the heat generally lets you dissolve way more solute. All right, Section 4, the art of separation. This is where things get really fun. Let's start with a process that almost feels like a magic trick, sublimation. Imagine you've got a mixture of sand and camphor.
Camphor has this really weird, unique physical property. When you heat it, it skips the liquid phase entirely. It just goes straight into a gas. So if we heat this mixture, the camphor vaporizes, totally leaves the sand behind, and then cools back down into a pure solid state.
If you set this up in a lab, as the china dish heats up, the camphor turns into a vapor. You just pop an inverted glass funnel over the dish with a little cut-and plug at the top so the gas can't escape. As the vapor rises and hits the much cooler glass walls of the funnel, boom, it deposits right there as pure, solid white crystals, completely separated from the leftover sand at the bottom.
Okay, but what if we have two liquids perfectly mixed together, like water and acetone? We can't exactly run that through a coffee filter. Instead, we use distillation. This method relies entirely on the fact that different things boil at different temperatures. We heat the mixture up. The liquid with the lower boiling point turns to vapor first. We catch that vapor, cool it down in a condenser, and collect it as a perfectly pure liquid in a totally separate flask. So, when you heat an acetone water mixture, the acetone boils at just 56 degrees Celsius, which is way before water hits its boiling point of 100 degrees. The acetone vapor rises, gets forced into this long, angled glass tube called a water condenser. Cold water is continuously circulating around the outside of that tube, sucking all the heat out of the vapor, turning it right back into liquid acetone, which then drips safely into a fresh flask on the other side. It's incredibly elegant. Sometimes, though, nature just hands us a freebie. What if the liquids don't mix at all, like oil and water? Chemists call these immiscible liquids. You literally just pop them into a separating funnel and rely on good old-fashioned physics, density. The water is heavier, so it sinks right to the bottom. The mustard oil forms a distinct yellow layer floating on top. To separate them, you just turn the little stopcock at the bottom, carefully drain the water out, and stop it just as the oil reaches the spout. Done. And then there's paper chromatography, which is just a highly visual, beautiful technique. You put a single spot of black ink on a strip of special paper and dip just the very bottom of that paper in water. As the water creeps up the paper, it physically carries the ink with it. But here's the secret. Black ink is actually a mixture of a bunch of different colored dyes. Because these dyes interact differently with the paper, they travel at different speeds. So as the water rises, that single black spot separates out into a gorgeous vertical rainbow of its individual colors. Finally, let's bring it all home with Section 5, Chemistry in the Real World. Think about centrifugation, spitting a mixture incredibly fast so the heavy stuff gets pinned to the bottom. Now, modern hospitals use these high-tech, expensive electric centrifuges to separate donated blood into plasma, white cells, and red cells. It's totally vital for medical treatments. But then, look at the paperfuge. It's a hand-powered device made out of literal cardboard and string, inspired by an ancient spinning toy. It costs pennies to make, needs absolutely zero electricity, and yet it spins fast enough to separate blood and detect diseases like malaria in remote, under-resourced areas. It is just a brilliant, life-saving application of separation science. And the sheer scale of this science is mind-blowing. Take distillation. You've got the traditional Deg Babka method in India, where for generations they've used these gorgeous metal pots to capture the earthy scent of the first rain or extract delicate flower fragrances for perfumes. Now contrast that ancient, beautiful art with a massive modern petroleum refinery. It takes raw, thick crude oils straight from the earth and uses fractional distillation to separate it into petroleum gas, petrol, kerosene, and diesel. The very exact same scientific principle of boiling points is what captures a delicate perfume and powers the heavy industries of our entire planet. And let's not forget, humanity didn't invent separation. We just finally learned how to harness it. It happens in nature constantly. Your own kidneys, they are highly complex filtration systems working around the clock, continuously separating and removing waste from your blood. On a macro level, environmental sewage treatment is basically just massive sequential separation chemistry. We use sedimentation, coagulation, and filtration to turn human waste back into clean, usable water for the planet. Which really brings us to the very edge of what we currently know. As we master the art of pulling mixtures apart and truly understanding their exact colloidal properties, scientists are starting to ask the big questions like, can we reverse engineer this? Can we take everything we know about mixtures and create something like artificial blood that works just as perfectly as the real thing for any patient? It is a staggering, monumental challenge. But understanding the exact nature of mixtures, that's the very first step on that journey. Thank you so much for joining me on this explainer. Keep questioning, keep learning, and I'll catch you in the next one.